In this new series, we're going to be looking at parabolic curves. We're going to also be talking about them as quadratic equations. This is in contrast to our first series where we were looking at linear equations. In that set of videos, we're looking at y equals mx plus b. In this quadratic equation, you can see here, we have an additional term, this x squared term. This x squared term makes it parabolic. It makes it our quadratic equation. So our equation is y equals ax squared plus bx plus c. And we're going to focus on how changing the constants a, b, and c change the shape of the curve. And then we'll look at also in this series different applications where this shows up in engineering problems. In this series of videos, we'll be looking at different kinds of problems you might get when we're looking at quadratic equations. Here's an example of a graph that shows a quadratic equation. It's parabolic. You've probably seen some of these graphs before. Now, you can be given points and asked to graph or identify an equation. Right? If you're looking for an equation and you're given facts about a graph or shown a graph, right? So you have how many unknowns? In that case, 3, 1, 2, 3, A, B, C. So then you would need to know 3 things about the graph, maybe 3 points or 3 facts. And we can look at facts from a lot of different perspectives. And we'll look in the series of videos all of these different types of problems. Now, this is looking at purely from a mathematical perspective. Obviously, we will be able to apply it to engineering applications, but they're using the same principles of solving it mathematically. That's why we're going to start there. Some common questions that you'll find is, how do you identify where a max or minimum is occurring? Now, the good thing about these quadratic equations is you know that you'll only have one maximum and one minimum point. That's the nature of these parabolic curves. You can also be asked to identify when the graph crosses the boundaries or the axes, x or y axes. And we'll do a bunch of example problems showing how to solve for that. You can also be asked if it does cross or doesn't cross the boundary, right? We can imagine that we can get a graph that might look something like this. And it will never cross the x-axis, but it will cross the y-axis eventually. What we won't look at are parabolic curves that are tilted, right? We're not going to look at any graphs that are tilted like this. And we're not going to look at graphs that maybe look something like this, right? If it's rotated 90 degrees, instead of having it be y equals ax squared plus bx plus c, this would have the form of x equals ay squared plus by plus c. And so we're not going to look at, let's see, what color should I use? I'll use green. So we're not going to look at these, and we're not looking at these forms. They can exist, obviously, but the good thing is we can always take our axis and just rotate it. And so we can always change the graph. Now, this one here, the x equals ay squared plus by plus c form, that essentially is allowing us to have multiple points at a given y value. This form doesn't allow that, right? You only, at any x location, you only have a single y value. But any y location, you can have up to 2 x values that represent that y point. And so we'll look at why that shows up, and then what applications we can actually apply when we are looking at engineering problems or physics problems that have a quadratic behavior. Some common sense but important things that we'll notice when we look at these quadratic equations are that once we identify, in this case here, these 3 equations, we have minimums. Once we identify where the maximum or minimum location is, we know that we have a mirroring effect, right? So if I, for example, let's look at this red curve right here. This red curve is described by the equation y equals x squared, the simplest form of quadratic equation that you usually start by looking at, right? So this would be represented by a value of 1, a b value of 0, and a c value of 0. So y equals x squared. Once we identify the minimum, at least graphically, you can see that that occurs at x, or at the origin, right? X equals 0 and y equals 0. Then I could draw a vertical line. In this case, it's nice because it's just this y-axis. And I know that there's going to be symmetry. It's just going to mirror over, right? So if I fold this screen over along these axes, this red line will fall right along this other red line. That's important, right? We'll see a lot of engineering applications where we want to know where the line of symmetry is for either something geometric, right? Something physical, or maybe conceptual. Maybe it's across time, something is happening, and we'll look at those kind of examples. But once we start looking at things where b and c are not equal to 0, in this case, like this blue value, when I put b equals 1, a equals 1, and c equals 0, we see that the curve shifts, this graph shifts. And then when we add a constant value, we see a shift occur again. So we'll have some videos looking at why these shifts happen, how we can predict when these shifts happen, and how, using that understanding, we can compare graphs, compare equations once we understand the relationship between A, B, and C changes.